Okay, now it started. Yeah, I'm sorry. So if next time onwards I forget to record the meeting, just let me know, because yeah, sometimes I may do that and forget, and meeting may not get. Okay, so let me say. Yeah, so what I did today was, let me brief up. Last time I showed you how to generate an observation from the original distribution given a sufficient statistic. Then today I started doing this example where a probability mass function is given in which sample space is x1, x2, x3, and the parameter space is theta1, theta2, theta3. I had to find a sufficient statistic in this situation. So what I did was I tried to find out what is a sufficient partition in this case. And we know that a partition P, which is PT, T belonging to lambda, will be sufficient if probability that x equal to x, given that x belonging to PT, does not depend on theta. So let me write down this range of T as tau, so I can denote this by. So if I have to show that probability x equal to x, given that x belonging to PT does not depend on theta for every T belonging to tau and x. Then I look at the example, what is the f theta x given P1, which is probability that x equal to x, given that x belonging to P1. X belonging to P1 means x is in the set 1 and 2, so which is same as probability that x equal to x, given that x belonging to x1 and x2. Now, which is same as this quantity. For x equal to x1, this will be same as probability x equal to x1, given x belonging to x1 and x2, which is same as probability x equal to x1, comma x belonging to x1, x2 divided by x belonging to x1, x2. Intersection of this is same as probability x equal to x1, and then probability x equal to x1 plus probability x equal to x2 under theta 1, which turns out to be 0.4 upon 0.4. And similarly, you can find p theta 1 that x2 belong to p1. And then you observe that f theta x given p1 does not depend on theta. Similarly, f theta of x given p2, which was straightforward to find, also does not depend on theta. So I could get a sufficient partition. I could prove that x1, x2, and x3 is a sufficient partition. So a statistic, any statistic P which gives the same value to x1 and x2, and a different value to x3 would be sufficient. And then we saw that if I consider a statistic which gives the same value to x2 and x3, which is 1, and a different value to x1 is not sufficient. So now let's try to develop a criteria for finding a sufficient statistic. So let FF and GF respectively denote the PMF or PDF of X and TX, and X has a distribution F. You see, X, the distribution of X is not known. So X has some distribution F belonging to P. If X has a distribution F belonging to P, I denote the PDF of X by FF and PDF of TX by GF. Let T be in the range of statistics T, says that probability that Tx takes value T is positive. Then probability x equal to x given Tx equal to T, note that if T was sufficient, it would be independent. Probability x equal to x given Tx equal to T would be, now note that this is same as probability that x equal to x, Tx equal to T, divided by probability that Tx equal to T. So note that if Tx is not equal to T of small x, which is T, then this quantity would be 0. Because this says that T of x should be same as T of small x. This says T of x should be same as T. So if T of small x is not same as T, the two events cannot occur simultaneously, so this quality would be 0. Whereas if t of small x is same as t, then this event implies this event. So this intersection probability would be same as probability x equal to x, and in the denominator you have tx equal to t. So if tx equal to t, then this probability would be the ratio of these two probabilities. And you know that t is sufficient if and only if this quantity is independent of theta. So thus tx is sufficient for f if for every x belonging to chi, probability x equal to x, given tx equal to t, or tx equal to t here is same as tx, or tx equal to small t capital X equal to t small x does not depend on f. Or equally, tx is sufficient for p if for every f belonging to a p and x belonging to x, such that g of tx is positive. This is g of tx. F of fx divided by g of tx is constant in f. That means it does not depend on f. So that means it should be some function which only depends on h. So that is what I'm doing in the next theorem. Tx is sufficient for p if and only for every x belonging to chi. G of x upon g of tx is constant in f over all those f such that g of tx is positive. And once I have this, then I can prove the factorization theorem, which says that tx is sufficient for p if and only if there exist functions psi f and h, such that for all x belonging to chi and all f belonging to p, f of fx is same as psi of tx into hx. The proof, in fact, I have already proved. I have shown that tx would be sufficient if and only if this quantity does not depend on f. So that means f of fx upon g of ftx same as some quantity which does not depend on f. So I can call this as hx. So that means my statistic t would be sufficient if and only if the joint PDF of x can be written as gf of tx if you want, this can always be written as psi f of tx into some other function, let us say. Let me call this as h1x. And I call, because I can consume some of the h1x g of tx, because psi f is not unique. You can take psi f to be same as gf and h to be same as h. But if you want, you can subsume some part of h1 into g of tx, and remaining you can take as hx. Still, you get some function psi f which have some part of h1x along with being dependent on f. So this gives you a factorization theorem. So f of x is same as psi of tx into hx. So my statistic t would be sufficient if and only if my joint PDF of ff can be written as a function of unknown distribution along with sufficient statistic into a function which does not depend on f. Now, in the case of parametric family, what would be this criteria? If I have my densities f theta, then T is sufficient if and only if f theta x is same as psi of theta tx, because in the parametric family, this f gets replaced by the theta because f is completely known, except that I may have unknown parameters. And this is what the factorization theorem says. So now you have developed a very nice criteria for sufficient statistic. Now here I have formally given a proof, which in fact I have repeated here itself. So let me not go through this proof again, because I've already given a proof. Let me make a few remarks Suppose my P0 is a smaller family than P. And if Tx is sufficient for larger value, then larger family, then Tx would also be sufficient for the smaller family. Why? Because if the conditional distribution of X given T does not depend on any F in P0. So it is P0, it is P1. P. So what if X is sufficient for P, then I know that T is sufficient for P, then I know that conditional distribution of X given T is same for every element in P, because it does not depend on elements of P. So if it does not depend on elements of P, it will be constant in P0s. So that means conditional distribution of X given Tx would be the same for all elements in P0s, because it is constant over whole P. So this proves that if P0 is a subset of P, and if T is sufficient for a larger family, then T would also be sufficient for a smaller family, just by the definition. Another thing which you can note is Tx, the whole sample is always sufficient. Now, proving this is not difficult. Why? Because how do you prove it? Because if you look at f of fx, this can always be written as psi f of whole x into hx, where my hx is 1 and psi f x same as the density itself. So I can write down f of x as psi of x into hx. And by factorization theorem, I know my statistic T is sufficient if joint PDF is same as psi f of a function of T and hx. And hx should not depend on f. And that is what exactly I have done over here. F of x can be written as f of x itself. So I can take my psi of x as f of x and hx as 1. So what is the role of Tx over here? The role of Tx is x itself. Just compare with this. So here Tx is same as x. So this says that my x is a sufficient statistic all the time. And that you can do it using definition also. Conditional distribution of x given x would be a degenerate distribution. The whole sample is always sufficient. Now let's look at this one. If Tx is sufficient for f and Tx is a function of u, then u is also sufficient. How do you prove this? T is sufficient. What does that mean? That means my f of x can be written as psi f of Tx to hx. Because T is sufficient, so there exists function psi f, and h says that f of x is same as psi f of Tx into hx. But my T is given to be a function of u. So my T of x is a function of u. So that means k of u of x. T is a function of u. So T is some function of u. Now, if that is the case, then I can write down my f of x as psi f of k of ux into hx. Now I can write down this composition of psi f with k as psi f star. Then this can be written as psi f star of ux hx. What you have been able to write down? You have been able to write down the joint PDF as product of two functions, one of which only involves f and ux, and the other one does not involve any f. So then by factorization theorem, is implied that u is also sufficient. This is a very nice thing to know, that if T is sufficient and you can get T from u, then u is also sufficient. T is a function of u. What does that mean? Given the value of u, you can get T. That is what it means. T is a function of u means given the value of u, you can get the t. So for example, if x bar is sufficient, then let us look at order statistics x1, x2, xn is also sufficient. Why? Because if x bar is sufficient, I can get x bar from these xi's. I know x bar is same as summation I is equal to 1 to n xi, which is 1 by n. Whether you sum all xi's or sum all order statistics, the sum is same. So this is same as sum I is equal to 1 to n xi. So through the values of xi's, you can get x bar. So that means x bar is a function of these order statistics. And since x bar is sufficient, so these order statistics will also be sufficient. Similarly, let us look at this example. If x bar square is sufficient, then mod of x bar is also sufficient. Because you can get the value of x bar square by squaring the mod of x bar square. By squaring the mod of x bar. So x bar square is a function of mod of x bar. Because x bar square same as mod of x bar. Because x bar square is a function of mod of x bar. And since x bar square is sufficient, mod of x bar would also be sufficient. Now note that x bar is sufficient may not imply that x bar square is sufficient. Why? Because you cannot get the, you see, if I was able to get x bar from x bar square, then I can directly say. But given the value of x bar square, I cannot get x bar because x bar square, you know, then x bar could be minus square root or plus square root. So there could be two possible values of x bar which correspond to the same x bar square. If x bar is sufficient, I cannot say that x bar square is sufficient unless x bar takes only positive values. X bar greater than or equal to, unless probability that x bar greater than or equal to 0 is 1 for every f. Because if x bar only takes positive values, then given x bar square, x bar is nothing but a positive square root of x bar square. So now let us look at some examples. So let me quickly go through these examples. Let x1, x2, xn be a random sample from binomial 1 theta distribution, where theta is in 0 to 1, so that tx is sufficient for theta. Or t1 fx, t1x equal to x bar, t2x equal to x bar square, and t3x equal to x bar plus 5 sufficient for theta. So you can just see very quickly, my x1, x2, xn is a sample. Each xi is because binomial 1 theta. So each xi can take value 0, 1. So x1, x2, xn together can take value in the sample space chi, which is Cartesian product of 0, 1 n times, 0, 1 to power n. So basically, x1 take value 0 to 1, x2 can take value 0 to 1, and so on. Xn can take value. What is joint PDF? F theta x, because they are given to be independent. Because it is a random sample, so it is a product I is equal to 1 to n. And then the probability density of xi at the point small xi. Each xi have a same distribution, which is binomial 1 theta, And binomial 1 theta has a PMF, theta to the power xi, 1 minus theta to the power xi. I do this becomes theta to the power summation xi, 1 minus theta to the power n minus summation xi. So this clearly can be written as psi theta xi times hx, which is basically psi theta of tx into hx, because it is a function of all, this only involves theta and summation xi. Where my hx is 1, if x is in the sample space, 0 to 1, so if x belongs to 1, 0 otherwise. My psi theta t, psi theta t is theta to the power t into 1 minus theta to the power n minus t, if t is between 0 to n, because summation xi can take value 0, 1, 2, and so on, and 0 otherwise. So you have been able to write down joint PMF as function of theta and summation xi and a function of x. So this says that summation xi is sufficient for theta. Note that since xi's take only value 0 and 1, tx is always greater than or equal to 0, because xi's can take value only 0 and 1. So tx is always greater than or equal to 0. Now, given the value of x bar, I can get summation xi. So tx, which is summation xi, is a function of x bar, because n times x bar is same as summation xi. So x bar is also sufficient, because you can get t from x bar. And you know that t is sufficient and t is a function of u, then u is also sufficient. Now, if x bar is sufficient, and I know that x bar is always greater than or equal to 0. If x bar is greater than or equal to 0, I can get x bar from x bar square. So if x bar is sufficient and x bar is a function of x bar square, because x bar is positive or non-negative, so x bar square is also sufficient. X bar plus 5, because x bar plus 5, x bar is sufficient, and x bar is a function of x bar plus 5, because you can get x bar from x bar plus 5 by just subtracting 5 from this. So they are all one-to-one functions. It follows that t1x, t2x, and t3x are also sufficient. Let us look at another example. Suppose I have a random sample from normal mu sigma square, where mu and sigma are both unknown. So theta is mu sigma, which belongs to r cross 0 to infinity. So that summation xi and summation xi square is sufficient statistic for theta. T1x equal to x bar square is sufficient for theta. Where x bar is sample mean, s square is the sample value. So the proof is straightforward. I just try to look at what is the joint PMF, which is product I is equal to 1 to n, 1 by sigma root 2 pi, e to power minus 1 by 2 sigma square. There will not be a sum over here. Sum would combine this product. So this quantity. It becomes 1 by sigma root 2 pi to power n, e to power minus 1 by 2 sigma square, and summation xi minus mu whole square. Summation xi minus mu whole square can be written as xi square minus 2 mu summation xi plus n mu square. So now I have been able to write down. Note that now xi has been summarized everything in terms of summation xi and summation xi. So my f theta x can be written as psi theta of summation xi and summation xi square into hx, where my hx is 1. And what is my psi theta of t1 and t2? It is 1 by sigma root 2 pi to power n. Note that I cannot consume this 1 by sigma root 2 pi to power n in hx, because sigma is unknown here. If it was known, I could have consumed this also in the hx. E to power minus 1 by 2 sigma square, then summation xi square, which is t2, minus twice mu summation xi, which is t1, plus n mu square. T1 is in R and T2 greater than or equal to 0. because summation xi square would be given, and 0 otherwise. Now note that if my sigma was known, then T2 upon 2 sigma square also could have been consumed with Hx, because then Hx does not have any unknown parameter if sigma was. And then only T1 would have played a role, and a sufficient statistic would have been just summation xi, not the two. Similarly, note that if mu was known, if mu was known and sigma square was unknown, then summation xi minus mu whole square could have been considered as a one statistic because mu is known. So if mu is known, summation xi minus mu is whole square would have been a sufficient statistic. All the three cases, in fact, you can cover from here. So summation xi square is sufficient for f when sigma, mu and sigma are both unknown. Now, Tx and summation xi square is a one-to-one function of x bar and s square. Why? Because x bar and s square is same as 1 upon n summation xi and 1 upon n summation xi square minus x bar square. Right? You can get this summation xi and summation xi square from this. How do you get it? You multiply the first component by n, you get summation xi. You look at the second component. In the second component, you add the square of the first component, you get 1 upon n xi square. And whatever you get, you multiply by n, you can get this. So you can get t from x bar square, and t is sufficient. So this would also be sufficient. In fact, both are one-to-one functions. You can get this from this also. Now, since t is sufficient and t is a function of u, which is x bar s square would also be sufficient. Now, let me make this small note over here because I have already covered that if sigma is known, then I have seen that if sigma is known, that T2 only depends on observation, and sigma is known, which is a known quantity. So I have consumed this T2 upon 2 sigma square also in Hx, because that would then only be a function of x, because sigma square is known. Then by factorization theorem, I would have written this as a function of mu and T1. So in that case, T1 would have been sufficient, which is summation xi. Now I can come back over here. If mu was known, I would have written this as sigma root 2 pi to power n e to power minus 1 by 2 sigma square summation xi minus mu whole square. So if mu is known, summation xi minus mu whole square is a sum statistic, Ex. Then I would have written this as psi of sigma square and summation xi minus mu whole square into Hx. So summation xi minus mu whole square would have been a sum statistic. Sigma is known, then I know that summation xi is sufficient. If summation xi is sufficient, x bar would anyway be sufficient. Mu is known. Now sigma is known, that means only parameter is mu. So summation xi is sufficient for mu. If mu is known, that means only parameter is sigma square, then summation xi minus mu whole square is sufficient of sigma square. So all the three cases I have covered over here. Sigma is known, mu is known, sigma, mu both are known. Now let's do this example. Let x1, x2, xn be a random sample from uniform distribution on the set 1 to theta, where theta is in take integer values 1, 2, and so on, and it is unknown. I have to show that xn, which is maximum of x1, x2, xn, is sufficient. Then I'm asking whether e to power xn is sufficient for theta. Now note that my sample space, because each of them can take value 1 to n, x1 can take value 1 to n, 1 to so on. x2 can also take value 1 to so on. And finally, xn can also take value 1 to 2. on. So my sample space is 1 to n Cartesian product of 1 to n. 1 plus 1. What is my joint PDF? Is a product of each of them, because each of them has a uniform distribution, a discrete uniform distribution on 1 to theta. That means the density is 1 by theta. So the product would be 1 by theta to the power n. If each xi, let us try to see how can we. So you see, sufficiency says that you try to summarize the data. And all the information about the data is contained in the PDF. So I try to summarize all the xi's in the PDF. I try to put xi's in a very compact form. That is what actually it amounts to saying. So it is 1 upon theta to the power n. Now the theta is related to xi only this. Xi can take value any integer values. So I put xi takes 1 to 3n. But the only condition is my each xi should be less than or equal to theta. So if I have to summarize this information, this can also be written as each xi takes integer value. But condition is xi should be less than or equal to theta for every I. But each xi is less than or equal to theta for each I means maximum is less than or equal to theta. So this I have summarized through maximum less than or equal to theta. And xi belonging to 1, 2, I have kept as. So what is this? This is a function of xn and theta. So f theta x is same as psi theta of xn into hx, where I can write down hx as 1 if xi belongs to 1, 2, and so on, and 0 otherwise. Psi theta t as 1 by theta to the power n, should be 1 by theta to the power n, if this t is less than or equal to theta. If t is equal to xn is sufficient for theta. So I've been able to, by factorization theorem, I've been able to write down this as psi xn into hx, where hx is given by this, psi theta is. Thus xn is sufficient for theta. Since e to power xn is a 1-to-1 function of xn, so given e to power xn, you can get xn just by taking the law. If xn is sufficient, e to power xn would also be sufficient, because any 1-to-1 function of a sufficient statistic will always be sufficient. So e of xn will also be sufficient. Now, sufficient statistic may not always provide substantial reduction in data. For example, in the last example, I saw that my whole data was exponential to xn. I could get a sufficient statistic which is only one dimensional, which is maximum of exponential. So from n-dimensional data, which was exponential to xn to begin with, I could get a one-dimensional data. In the last example, in the normal one, when mu and sigma square both were unknown, from an n-dimensional data, I could get a sufficient statistic which is only two-dimensional. So there is a substantial reduction in the data, substantial summarization of the data. But that may not always be the case. Not always sufficient statistics would be in a position to summarize the data. So let me stop over here. I can start from here tomorrow. This is end of lecture. If some of you have any doubts, you may ask it. Others may leave if they want. Please tell your colleagues that I'm seeing only 16 students present today. That's not a healthy sign. I'm not taking attendance just because I trust you that you would be sincere in taking the lectures. I'll not be in position to help you out if you don't do in exams and don't attend lectures also. So please tell your friends that this is something that I have noted. I don't mind if none of you come. If you can study of your own, fine. But don't expect any mercy in the exams in that case. Because then I'll assume that you are much smarter than me. and you can manage things of your own. So I don't mind if you don't come, but then you should feel that you are responsible for your acts. Nobody is going to help you. Okay, so that's all for today. If those of you who have any doubts may stay back, others may leave.
Excuse me, sir.
Yeah.
So on page number 4, there was some one step in this file. So where we have drawn an observation y for x given tx.
Page number 4.
Yes, sir.
Yeah. Yeah.
So on the upper part.
What part? Yeah.
Yes, sir. Yes, sir.
Yeah.
So
Yeah.
here from step number 2 to step number 3, can you explain it once more?
Step number 2 to step number 3.
3. Yes, sir.
Okay. So if you look at what I'm doing, suppose that Tx equal to T is observed, right? I'm saying that generate one observation, say Y, from the conditional distribution of X given Tx equal to T. What that means is, if Tx equal to T is observed, that means probability that Y is equal to X, given that Tx equal to T, right? If T is observed, that means given Tx equal to T, I generate one observation from the conditional distribution of X given T is equal to T. So this would be the same as probability that X equal to X. That is what it means. Because it says if you observe T, what you do is you go back to your computer and generate one observation from the conditional distribution of X given Tx equal to T, and I'm calling that as a Y. So if Y is a random variable, what it means? The distribution of Y given Tx equal to T, same as distribution of X given Tx equal to T. Right? That is what it means. This whole discussion boils down to saying this. Then for X belonging to chi, what you have is probability Y is equal to X is same as summation T belonging to T, Y is equal to X. Now, Y is equal to X depends on what observation I have observed. So Tx equal to T, and I sum over all possible values of T. So this is same as probability Y is equal to X, given Tx equal to T, times probability Tx equal to T. But probability Y is equal to X because my Y is coming from the same distribution as that of X given Tx equal to T, given that Tx equal to T. So this is same. So this is what it is. This is same as probability X equal to X given Tx equal to T, probability Tx equal to T. But this is same as probability X equal to X, again by the theorem of total probability. Does that clarify your doubt?
Yes, sir. Thank you, sir. Sir, and one more thing in problem set, there was one question, question number 7, I think.
Okay. Regarding?
Not question number 7, it was question number 8. It was regard. So I need to just see the question number.
Question.
Give me
Let me see. Can I stop this now?
Yes.
I can stop sharing this. Okay. Then you're saying that I should go to. Let me see.
It is question number 7.
Let me just check. So I don't have my homework here with me. Actually, I should go to the portal possibly. I should go to the portal. And Yeah, which question you're saying? Question
So
number?
question number eight.
8. Okay. Yeah. So what is the doubt in question number 8? What do you want to ask? Question number 8. Can you see the 8 now?
Yes, sir. So
Yeah.
it would be a lengthy process by using this Jacobian and stuff. So can I go to some shorter method which you can suggest?
There is no shortcut method. You have to go by Jacobian. Should not be very lengthy. Why? Why you are finding lengthy?
I think then I may have made some mistake.
The Jacobian would be very short. How do you start?
So I proved it that yi's are this exponential theta, and then I will just assume from y1 to yn.
No, yi's may not be exponential theta, no? Because yi's would be ID exponential theta. That is what you have to prove.
I was just having problem in showing that they are independent. That's it. So because if I see, so the problem here is if I assume two yi's, let it be yi and yi plus 1, then I will get 3 order statistics, xi minus 1, xi and xi plus 1. So I have done shorter course in probability theory and this order statistics. I know about it. So we have been taught to carry out to find out PDF of XR and XS, but not for 3 or more. So what will be the procedure?
You know the joint PDF of x1, x2, xn?
Of course. So it will be n factorial and PDF of x1, x2, xn.
Then there is no problem. Because joint PDF, let me use the whiteboard. That will be better. Okay, so let me just so let us look at the joint PDF of let us look at the joint PDF of let us look at the joint PDF of x1, x2, xn, right? At the point small x1, small. Will be factorial n, as you said. And the product of each of them is e to power 1 upon theta e to power minus
x by theta.
Right? So it is theta to power n e to power minus summation xi by. And the range would be 0 less than x1 less than x2 less than xn less than infinity. Is that okay?
Yes, sir.
Right. Now I'm making a transformation y1 is yi as n minus I plus 1 I minus xi minus 1, right? Right? Is what the transformation is?
Yes, sir.
So what does that say? If I have to make it in this term, y1 is same as n times x1 minus x0. x1 is here is small x1, right? So it is just n times x1, right? y2 is how much? N times, sorry, n minus 1. y2 is same as n minus 1 times x2 minus x1. Is that okay?
Yes.
y3 is same as n minus 2 times x3 minus x2, right? yn is same as 10 minus xn minus 1. Sorry. Because I have to get it from this PDF. In this PDF, first order statistic is fixed as small x1 and last one is xn. So that is why I have kept here. So what do you get? Your x1 is y1 upon n. x2 is how much? y2 upon n minus 1 plus x1, which is y1 by n. So y1 upon n plus y2 upon n minus 1. What is x3? x3 is y3 upon n minus 2 plus x2. x2 is this. So this is y1 upon n plus y2 upon n minus 1. n minus 1 plus y3 upon n minus 2. Keep on doing it. Finally, what would be xn? y1 upon n plus y2 upon n minus 1 plus y3 upon n minus 2 plus yn upon 1, right? That is what? With y3 over n minus 2, so with yn we will have 1, because xn would be yn plus xn minus 1. Xn minus 1 is coming from the previous steps. So what would be my Jacobian? x1 by del y1 is 1 by n, 0, 0, 0, 0, 0. Del x2 by del y1, 1 by n. Del x2 by del y2 is 1 upon n minus 1, 0, 0, 0, 0. Del x3 by del y1, 1 upon n. Del x3 by del y2, 1 upon n minus 1. Del x3 by del y3, 1 upon n. So on. 0, 0, 0. And so on. Finally, 1 upon n, 1 upon n minus 1, 1 upon n minus 2, 0, 0, 0. And finally, here 1. And how much is this?
N factorial, 1 by n factorial.
1 by n factorial, right? And your range is 0 less than x1 less than x2 less than x. So I just see the range 0 less than y1 upon n less than y1 upon n plus y2 upon n less than y1 upon n, sorry, y2 upon n minus 1 plus y2 upon n minus 1 plus y3 upon n. So on. Keep on doing it up to the last one, y1 upon n, y2 upon n minus 1. What does this inequality give? This gives me y1 greater than 0. Right? What does the second inequality gives? I look at the first inequality, it only gives y1 greater than 0. What does the second inequality gives? y2 upon n minus 1 is greater than 0. So y2 greater than 0. What does the third inequality gives? y1 upon n, y2 upon n minus 1 gets cancelled. So y3 upon n greater than 0, which is same as y3 greater than yn greater than 0. What is the summation xi? Summation xi you can see from here, x1 plus x2 plus xn. y1 upon n, y1 upon n, y1 upon n gets added n times. Summation xi will turn out to be same as summation y. Because y1 upon n, y1 upon n, y1 upon n gets added n times. So that becomes y1. y2 upon n minus 1, y2 upon n minus 1, y2 upon n minus 1 gets added n minus 1 times. That would give y2. So summation xi is same as summation y. So what do you get? You get the joint PDF of y1, y2, yn as factorial n by theta to power n into e to power minus summation xi is same as summation yi theta into Jacobian, which is 1 upon factorial n. Then the range is each yi positive. And what is this? This gets cancelled. And this becomes product I is equal to 1 to n, 1 upon theta e to power minus yi by theta. Does that solve your problem?
Yes, sir.
Right. Anything else?
Thank you, sir.
That's all?
Yes, sir.
Okay. Thank you.